Hi. In today's video, I just want to go through limits briefly to give a general overview, and then the next video, we'll go ahead and go through a few examples together. So first, I just want to start with the epsilon delta limit definition. It can seem a little intimidating, lots of Greek letters, but essentially it's just describing what a limit is in a bit more detail. And if you want the more simple version, we could say that a limit is just the value of f of x, or y, if you will, as x approaches some value. So let's take a look at a graph. This is in Desmos. Shout out Desmos. So as we can see, say I'm thinking about a limit if x approaches 1. I can look at f of x, or the y value, as x gets really, really close to this value at 1. Even if that's undefined, the limit will still exist. Essentially, the limit is I'm getting close, as close as possible to this point without actually being that point. So the value of f of 1 doesn't have to exist. The function does not have to be continuous for this limit to exist. And I could take a limit coming from the left or a limit coming from the right. In order for the limit itself to exist, I have to have the limit from the left equal to the limit coming from the right. So like we discussed in the graphs, I can have one-sided limits, right? I can have a left-handed limit, which just has this little minus sign up above the number. And this we would read as the limit is f of x as x approaches a from the left. And the same with the right, except instead of a little minus up there, I have a little plus next to the number, and that's just showing that I'm taking the limit coming from the right only. Big deal alert, this theorem right here, for the limit to exist, the left and right-handed limits must be equal. So they must meet. We can't have any jumps. We can't have any asymptotes, right? For that limit to exist, the limit from the left has to equal the limit from the right. One really helpful property when evaluating limits is our direct substitution property. So if the function is continuous at that point, doesn't always work, but it works enough that it's worth trying out, is you can just directly sub in this value of a. And again, we'll look at a few examples, but this direct substitution property just says if a is in the domain, right, so it has to be continuous at a, then I can just plug a right into my function and do that to evaluate the limit. So let's just quickly look at one more graph. And if it looks familiar, it's the same one that we discussed before in the Desmos, but now we're going to show it right here. So if I'm talking about the limit as x approaches 1 of f of x, we're going to name him f of x, what would that value be? So essentially the way I like to think about it is x gets really, really close to 1, right? As x is getting really, really close to 1, what is y? As x gets close to 1 of this function, y happens to also be 1. So the limit as x approaches 1 of f of x here is 1. And that is the same from the left as it is the right. So that limit does exist. These are just a few limit laws and special limits that are good to kind of keep in your back pocket, say for later. So these help with evaluating limits. There's a few that are really useful. So if we want to take the limit of two functions added together, we can do each of those functions individually. Same with finding the difference. If we have a constant in front, we can go ahead and pull him right on out. And then you could just have the constant in front, evaluate this limit by itself. Once I get an answer, I can multiply it by the constant. No big deal there. If I have two functions multiplied together, really cool thing about limits is I can actually break those apart. So I could just find the limit of that first function, find the limit of that second function, and then multiply them together to get that product. A lot of these just can make manipulating the limits into a little bit easier of a form to solve, and then we can get an answer if we couldn't in the full function. So this is the same thing, just with a difference. So again, I can just take individually each limit, divide them, obviously provided that the bottom here, this bottom limit, isn't 0. Few special limits derived from those limit laws is I can actually, if the function is raised to a power, I can go ahead and find the limit first and then raise that answer, that limit I find, to that power. So kind of think about it like pulling the power out, if you will. The limit, this is a big one, big deal alert again. Okay. The limit of a constant is always the constant. The interesting thing about this is I don't care what a is, right? Is x is going to 1? Is x is going to infinity? Is x is going to negative 1,000? Doesn't really matter, right? The limit of the constant is always going to be the constant itself. Limit of as x approaches a of x is a. Again, this is kind of coming from direct substitution, right? If I just throw that a in for x, I would get right back out a. Same here, is really just thinking about direct substitution and maybe how that might apply to polynomials. Again, this is just another kind of direct substitution, right? Throw an a in there, no big deal. And then this last one here kind of follows from this. I can make this a fractional power, if you will, and essentially just find the limit first and then take that power. A few common trig ones. These are great to memorize. A lot of these can be kind of tricky to derive, maybe using squeeze theorem, L'Hopital, which we probably don't know yet. So definitely helpful to have these in your back pocket and just kind of memorize them for later. So these trig ones are just helpful to have kind of to memorize when they come up so we don't have to go through all the heavy lifting of deriving them. And I will have this document as a PDF listed in the description box. So you're welcome to download this, keep it for later, reference it, and work on memorizing some of these properties. Okay, so that's it for our overview of limits, just some basic information on what a limit is and how maybe we can work to find it. So in the next video, we'll go through a few examples of what that actually looks like. Thank you so much for watching. Again, the PDF for all the notes is in the description box, as well as a link to my website for access to private one-on-one Zoom tutoring. Thanks again. Bye.